So what have we got here? We're going to look at, this is more the state of the art. So for example, if you buy mathematical software that does numerical approximation of solutions of differential equations, it probably uses Runge Kutta. So working with Hoyne's method, note that using only the first derivative, because remember what Hoyne does is it kind of says the next y value is equal to the previous y value plus step size over, and then step size over 2 essentially, because you're going to average two slopes. The previous slope plus the Euler predicted next slope. That's essentially, now the notation isn't great there. Maybe we could swap and put in a k plus 1. So we'll just zoom in there just see what I've actually done. So this is saying the next y value is the previous y value, step size over 2, previous slope, and then k plus 1, the next slope as predicted by Euler. Okay, and it only uses the first derivative. Now it uses two of them, but it uses only one of them. And note that it has a similar error estimate, local errors order h cubed, global errors order h squared, as the more sophisticated three-term Taylor method, which used second derivatives. And remember, calculating the second derivatives is a bit of a pain because you have to do implicit differentiation. It turns out that higher order Taylor methods, more accurate methods, so you can go to a four-term Taylor method, which needs a third derivative, which is local errors order h to the 4, which is really, really good. They can be reduced to first derivative methods. So all these good methods can be reduced. Instead of having to calculate second, third, fourth, fifth, sixth, seventh derivatives, you can just do with first derivatives. So basically, rather than using, as say a four-term Taylor does, a cubic to get from one point to the next, you can combine lots of slopes and just go along a line. So the thing is to calculate the appropriate slope. So in the case of Hoyne's method, the slope you use is you average two slopes. Okay, so let's kind of talk through this idea. Now this is going to be, we're not going to, okay, let's see. So consider initial value problem. So that's the derivative is given in terms of x and y. And we have some initial condition. Y of x0 is equal to y0. So the simplest example of this is when the derivative is a constant. Well, derivative is 0 is even easier, and then the solution is a constant. So this is, say, m, and y of, let's say, 0 is equal to c. Then you can show that the solution of this is y equal to mx plus c, which is a line. And if this, you use Euler's method, you get no error. So we can just kind of sketch this. So here's the true solution, y equal to mx plus c. It's a line. Now we can start actually wherever we want. We don't have to start at x equal to 0. We can start at x0. And if you go into x1, it doesn't even really matter what the step size is. So this would be x0, mx0 plus c. And you'll say to yourself, okay, what is the slope of the tangent there? You'll get it from the differential equation. It's a constant. So you'll move along the tangent for a distance of c. Sure, aren't you going to get exactly the right answer? So the error in the Euler method here is 0. Okay. So slightly more complex is the initial value problem whose solution is a quadratic. So this looks like the first derivative is equal to 2ax plus b, and the initial condition is y of 0 is equal to little c, and then you can write down the solution of this will be ax squared plus bx plus c. So that's a parabola or a quadratic. Okay, so now we're going to assume, I think, that the derivative is a function of x alone. It's going to be a lot easier. So we kind of have in our little example down here. So the solution here is, say, y equal to x squared plus 1. Okay, so I think we're going to draw this picture up above here. Okay, so this is just a condition that we're going to see. So occasionally you will have seen that I write dy dx equal to a function of x alone. Now what that means is it's just a condition to make the analysis a little bit easier, that I can actually do it with she. So this is a thing where no matter where the curve is, doesn't matter if it's there, 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 if I've drawn this properly, the slope only depends on x. And so at all of these places, the slope should be exactly the same. In this case, maybe slightly negative, if I drew it properly. So slope is independent of y. And in particular, this is good because if you have errors, if you're in the middle of some kind of numerical method and you have errors in the y values, when you get to this point, certainly when you're calculating the next slope, the errors aren't going to compound, because even if this is, say, the exact solution down here, and this is where the approximation is, at least you're going to have the right slope. Now I'm going to get rid of them because we don't really want them there actually. Okay, so it is a good thing. So an example, something like this. So now here's the question. If I've got a differential equation where the answer is a parabola, is it possible to get the exact answer? So like the Euler method is no problem. If the solution is a line, we can get zero error. But if the solution is the next most complicated thing, a quadratic, can we get the answer essentially with a line? Okay, and I think we're going to look at the picture on the next page and then go back to here. So what we have here is a plot of y equal to x squared plus 1. And here is some numerical method Now what we're saying is Euler's it's not Euler's method, because look, it should be using the previous slope, so it's not Euler anyway. And in general, what we want to do is it's going to use two slopes, like the Heinz method used two slopes. Okay, so the question is, how can we extract the slope? So if we look at this thing, if we look at the coordinates, say this is x equal to 0, y equal to 1, and this is x equal to 1, y equal to 2, and the rise over the run, the rise is from 1 to 2 is 1, the run is from 0 to 1 is 1, so the slope of this line is equal to 1. And the question is, how can we extract from the differential equation dy dx equal to 2x, how can we extract the slope of 1? And it's easier if the derivative is just in terms of x. So there's two methods that come to mind. The first is combine the slope here and the slope here. So the slope here would be 2 times x, 2 times 0 is 0. The slope over here, 2 times x, 2 times 1 is 2. And average them out and you get 1. So in this case, so what I'm saying here is that if the solution is a quadratic and you take a line as a numerical approximation that takes the slope at xi and xi plus 1, so at the current point and the next point. Now there's no predictors here because the derivative is independent of y. And if you average those two slopes, which is basically Heinz method, you get zero error. The other alternative that we can mention at this point is to cut it down the middle. So just take the midpoint, x equal to half. Now this is only using one slope, but it's using one slope twice, is the way I'd explain it. So it's like x squared, x minus 1 all squared equals 0 is 2 roots 1, but they're there twice. So same thing here. So at x equal to half, the slope will be 2 times a half. which is equal to 1. And that's what you call the midpoint rule. So we got the midpoint method represented here, and we've Heinz method. Now what we're going to learn is that you can actually pick any 2 points. So Heinz method picks the start and the end. So let's say xk and xk plus 1. The midpoint kind of uses what you call xk plus a half, but twice. But you can take any 2 points as it happens, and there's you can use the slopes at those 2 points and end up with m equal to 1. This is what we're gonna study. Okay, so here this is what we just went through. The slope of y equal to x squared plus 1 is 2x. Consider the slope at x equal to 0, x equal to 1, 0, and 2. The average of these one. What method is this? That's Heinz method. And then the other one is midpoint. Now it says not implemented, but you might have a look at it in your case study for assignment 1. Okay, now let's look at it in more generality. So denote by this phi x0h, the slope of the line required to always predict the correct value at the next point. So in this case, in this notation for this question, the initial point is 0 and the step size is 1, and we needed the slope to be 1. So it's a slope that you're trying to get. Now I don't have to go this in full. I mean the theory is interesting, but it's the summary at the end we'll be mostly concerned with. So denote by the slope of the line required to always predict the correct value when the solution is a quadratic. So what we're going to do is suppose that it's a combination of 2 things. So this is a weighted average slope. So this is K1 and K2 are both slopes. So K1 and K2 are slopes. And you want to think of them at some points. Now, I can't really say x1 and x2. That's not a good... The notation is just breaking down. So I'm just going to say at 2 points in between x0 and x1. So Hein would say the start and the end. Midpoint would say the middle twice. So, and then A1 and A2, these are weights. So with Heinz method, the weights are a half and a half. Half, your slope is coming from the start of the interval, half from the end. And the midpoint, well, you could argue the midpoint differently. You could say you take the midpoint and some other point, and the weights are 1 and 0. That probably makes more sense. So suppose that K1 is the starting slope. So you don't have to do this, but this is an option. So this is the slope at x0. Now you don't have to do this, I don't think, but we're gonna analyze it this way, and let K2 be the other slope. So you're going to take, try again. You got x0 and x1, and you're going to go a proportion of the distance between these two. So P is a proportion of h, because remember, the total distance between these two is h. And you're going to calculate the slope at this other point, K2. So it's some proportion of the distance along. If it's Hein, it'll be the full distance along, P equal to 1. If it's the midpoint, it'll be half distance along. So what you end up here is this is calculating the exact slope, because with a quadratic, you have the exact answer. So it turns out that this here is what you want to get. So this actually is phi of x0h. And the derivative here is 2ax plus b. Now, what the hell is going on here? So we're trying to get average 2 slopes. So this is the slope at x0. I need to delete that. That is correct, I think. I'm thinking about rubbing it out. So yeah, that is the slope we're looking for. Yeah, so I'll keep that. So this is the starting slope. Yes, that's good, because the differential equation is 2ax plus b. So you sub in x equal to x0. So that's the starting slope. And then what about this thing? So you're putting in 2ax plus b, but you want to substitute in this point here, which is 2a, and the x is x0 plus ph. You do some algebra, and you want these two things to be equal. So there's actually 3 unknowns here, but only 2 equations. So the first is if you compare, so we're trying to compare these two. So look at the number of x zeros. So in the first one, it's 2a times a1 plus a2, and in the second it's 2a. So the a1 plus a2 must be equal to 1. And then in the second thing, I think you're comparing, who knows what you're comparing. Oh yeah, so the second thing, if you compare the b's, look, this has to be equal to 1. That's the same equation, we already had that. And then you're trying to compare the multiple of h. So you want ah equal to a times this, and you might see that you need a2 times p to equal to a half. But there's actually 3 unknowns, as I said, but didn't go on. a1, the first weight, a2, the second weight, and then arguably p. But really what this is saying is if you choose p, you've got 2 equations, 2 unknowns you can solve. Okay. So what this is saying is that for any value of p, so you take the starting point and any other point, so you take x0 and any other point between x0 and x1, you can get this and have 0 error for quadratics. Okay, so we're just going to give something, so 0 error for quadratics for quads is, in a way, it's like the 3-term Taylor method. Okay, so here you get things. If p equal to 1, you end up with a1 is a half and a2 is a half. You end up with pi. Okay, so that means you're going to use the start, and p equal to 1 means the whole way across. If you pick, what is this? This is fine. If you pick a2 equal to 1 or p equal to half, you'll end up with a1 is 0, so you only use 1 point. This is called the midpoint. This means that there are loads of ways of doing what the 3-term Taylor method tracks quadratics correctly with 0 error, without the second derivative. Now things are more complicated when we have y dependence, and I think I've gone through you enough, but if you really wanted, you could kind of go through this, and you can see that there's actually loads of ways of doing it. Now this is one particular method. Maybe we'll look at it very, very briefly. So let's see, what does this seem to be doing? It seems to be doing, you pick 2 things. You pick, I have to be very careful here now, get this right. Don't want to talk raw-mate. Yeah, so you do pick the starting point. I think you could actually do it without even picking the starting point. So you pick starting point and a distance along the interval. And then the other point that you pick, you go, so I think it's implicit. So x0, x1. So you pick 2 points. You do x0 plus ph. And then I think you do an Euler predictor with that distance, I think, or so. Yeah, look, I know I'm kind of, I'm lost myself here. I should just stop talking. But use two points, this one and this one. I think it's in there, and yeah. So anyway, you can go through all this, and you end up that there's loads of ways of doing it. So one way is you pick a2 equal to half, p and q equal to 1, and that means that you end up with Hein's method. And similarly, if you pick a2 equal to 1, you end up with the midpoint method in full. Okay, Euler's method does not fall under this family. Okay, because Euler's method cannot track quadratic exactly. So basically, what a lot of that is complicated. What I want you to take away is we can do the same as the 3-term Taylor method if we use 2 slopes. And we average the slopes, a weighted average of the slopes, and we can do kind of similar to the 3-term Taylor when it comes to quadratics. Right. Now, how much we should push this. I think we should maybe look at the different equations, and then we'll go back to this summary next week. So there's all these different Runge Kutta. So the second order Runge Kutta methods are supposed to be like a 3-term Taylor method. Okay. So Heinz method will use x0 and x1, and it'll average the two slopes. So remember, these are slopes. And look, it's the slope at x, the starting point and the next point. Now where is, now remember here, now we do have y dependence. So the next point is easy, but what about the next y value? Well, use an Euler predictor. So what I'm saying here is you've x0, but you also, in general, you have y dependence. So this could be y0, and what you use x1 plus some Euler predictor. You compare those two. The midpoint method in full, it uses, what you need to do is you need to do an Euler predictor for the midpoint. So you do need this initial slope. So you travel along halfway. So now I'll use xi and xi plus 1. So you start at xi, you do an Euler predictor for what's happening at the midpoint, which could be called xi plus a half, which is equal to xi plus h over 2. And you look at this point here and you say, okay, what is the slope at this midpoint? Midpoint of the x is easy. What about the y? Well, we'll do a y predictor, or what we could call I plus a half. So we're going to use the Euler method to see what's going on at the midpoint. We got a pair of values x and y. The midpoint, there it's inside in the big bracket, it's there, and the Euler prediction for the midpoint, and we'll use that slope to go. Okay, using the same principles, we can derive higher order. So the common third order, so this is like a 4-term Taylor method. So that means the local errors of order h to the 4 and the global errors of order h cubed, which is really, really good. Like, so this means if you have an error, say h equal to 0.1, or let's say 0.5, and you go to 0.1, the errors are going to be reduced. So by a factor of 5 cubed. That's mighty. Now, what is actually going on here? It's a bit complicated, but it uses an average of 4 slopes. So this is kind of the slope at the starting point. This is the slope at the midpoint according to an Euler predictor. Then the K3 is a kind of an Euler predictor. We won't call it an Euler predictor, but this is the end point. And this is some kind of a mixed predictor. So you end up with, you have the starting point, a predictor for what's happening at a midpoint, and an initial predictor what's happening at the end point. You calculate the slope at those 3 points, and then you weight those slopes. So you take one of these, you take one of these, and you take 4 of these, and average them out, divide by 6, and look at the end. It's just the next value is previous value plus step size times this weighted average slope. Okay, and then the state of the art is this one. Now this is really, really great because it's global errors order h to the 4. So like you want to decrease your step size by a factor of 10, the errors decrease by a factor of 10,000. Now this is, so here, let's see what's happening here. So it seems to be using, I think we have a picture on the next page, which I can't really improve on. Yeah, so this is the 4th order. So it takes 4 different slopes. It calculates this slope. It does a predictor. So see, this uses K1. So this is a predictor. And then what it does is it takes the slope here and here, and I think it averages them out. Do I see that? No, I don't. But what it does do is it goes back to the start. See this slope? It goes back to the start and uses it here. And you get to another point, you calculate the slope there. And then you see what's the slope there, and okay, we'll go here. And then you calculate what the slope is here. So there's 4 slopes that are weighted. This initial slope, the slope here, then you use that K2 to find out a better approximation what's going on at the midpoint. Use and then find the slope there, and then use that slope we just calculated to estimate the slope at the end of the interval. So you got one slope at the start, which is kind of crap, and one slope at the midpoint, which is okay, an improved slope at the midpoint, which is even better, and then a slope at the end point, which is pretty hot, and then you average all of those slopes, and you use, what is it? So use one of these, one of them, one of them, two of them, and average them out, and you end up with this thing. Now, what happens? Why don't we go to 5th order and 6th order? Well, you can, but what happens is, as you're getting more accurate and accurate and accurate, the number of calculations is increasing quite a lot. I'm not sure exactly what happens, but my feeling is that when you make loads of these calculations on the computer, okay, you've got an issue with computational time, but I think the more calculations you're making, the rounding error becomes a factor, and possibly if you do like a 7th order Runge Kutta, you're making so many calculations, they're taking too long, and maybe the rounding errors actually beat the truncation errors. I'm not actually sure of that, but basically you can think of it just as it's getting too complicated. But if, like, say, state of the art, so this is what a lot of software packages would use. But if you really had a very important project that you really wanted to be sure, you'd use like the 5th order or even 6th order. Okay. In terms of the VBA implementation, it's actually very easy. We'll look at that, and I think, yeah, we'll have to do a little bit more than this. I'll do that in the next lecture.